The ampacity of a 10-32 screw is not a well-defined quantity. Its current carrying capacity depends on several factors. Firstly, the material of the screw, for example, whether it's made of copper, aluminum, or steel. Secondly, the length of the screw, as a longer screw will generally have a higher resistance and therefore a lower ampacity. Thirdly, the tightness of the screw, since a loose screw will have a higher resistance and lower ampacity than a tight screw. And fourthly, the temperature of the screw, with higher temperatures leading to increased resistance and reduced ampacity. Generally speaking, a 10-32 screw made of copper or aluminum might have an ampacity in the range of a few hundred amps under ideal conditions. However, this is a very rough estimate and should not be used for any critical applications. Several factors can significantly reduce the ampacity. Firstly, a loose connection increases resistance at the contact point, generating heat and further reducing the ampacity. Secondly, elevated temperatures increase the resistance of the screw material, decreasing its ability to carry current. Thirdly, corrosion on the screw or the connected surfaces can also increase resistance and reduce ampacity. When it comes to main bonding jumpers, it's essential to rely on manufacturer's instructions and testing. The manufacturer has the responsibility to ensure that the main bonding jumper is appropriately sized and tested for the specific application within their equipment. They perform tests to verify the jumper's ability to safely carry fault currents. In the case of a UL-listed panel, the main bonding jumper has been tested and listed by underwriters' laboratories, all meaning it meets specific safety standards and is adequate for the intended application. UL testing process involves subjecting the bonding jumper to various stress tests, including high current fault conditions, to ensure it can safely handle potential overcurrent events. Relying on the UL listing and the manufacturer's specifications provides assurance that the bonding jumper is suitable for its intended purpose. Trying to calculate the ampacity of a small screw like a 10-32 screw for use as a main bonding jumper is not a practical or reliable approach. The actual current carrying capacity in such applications is determined by a combination of factors, and it's best to rely on the tested and listed values provided by the equipment manufacturer and UL. Therefore, the ampacity of a 10-32 screw is highly variable and application dependent. Attempting to estimate it without considering all relevant factors can be misleading and potentially dangerous. Focus on adhering to manufacturer's specifications and relying on UL listings for critical components like main bonding jumpers to ensure electrical safety and proper functioning of the equipment. When dealing with electrical panels and their components, it's crucial to understand the role of the main bonding jumper. The main bonding jumper is a critical safety component within an electrical panel. Its primary function is to establish a low impedance connection between the grounded conductor, often the neutral, and the equipment grounding system. This connection ensures that, in the event of a ground fault, a path of low resistance is available for fault current to flow back to the source, allowing the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and interrupt the circuit, preventing electrical shock hazards and minimizing damage. The size and material of the main bonding jumper are crucial for its proper function. It must be large enough to safely carry the maximum fault current that could occur in the system. The material should be a good conductor, typically copper or aluminum, to minimize resistance and ensure efficient fault current flow. The National Electrical Code, or NEC, provides guidelines for sizing the main bonding jumper based on the size of the service entrance conductors. The NEC specifies minimum sizes for grounding conductors and bonding jumpers to ensure adequate fault current capacity. These requirements are outlined in NEC Table 250.102. For example, if the service entrance conductors are sized at 200 amps, the main bonding jumper must be sized according to the table, which would likely require a copper conductor of at least number 6 American wire gauge, or AUG. The physical connection of the main bonding jumper is also crucial. It must be securely connected to both the grounded conductor and the equipment grounding system. The connection points should be clean and free of corrosion to ensure a low resistance connection. Proper torquing of the connection hardware is essential to maintain a reliable connection over time. In electrical panels, the main bonding jumper is typically located near the service entrance. It connects the neutral busbar to the panel enclosure, which is then connected to the grounding electrode system. The grounding electrode system consists of components such as ground rods, ground plates, or metal underground water pipes, which provide a direct connection to the earth. This connection to the earth helps to stabilize the voltage of the electrical system and provides an additional path for fault current to flow back to the source. It's important to note that the main bonding jumper is different from the equipment grounding conductors. Equipment grounding conductors run with the circuit conductors and connect the non-current carrying metal parts of electrical equipment, such as appliances and machinery, to the grounding system. These conductors provide a path for fault current to flow back to the source in the event of a fault within the equipment. The main bonding jumper, on the other hand, connects the entire electrical system to the earth and provides a primary path for fault current to flow back to the source. In the context of UL-listed panels, the main bonding jumper is a critical component that is thoroughly tested and evaluated to ensure it meets safety standards. UL testing process includes subjecting the bonding jumper to high current fault conditions to verify its ability to safely carry fault current without overheating or failing. The UL listing mark on the panel indicates that the main bonding jumper meets UL requirements and is suitable for use in the panel. When installing or maintaining electrical panels, it's essential to follow the manufacturer's instructions and adhere to the NEC requirements for grounding and bonding. Improper grounding and bonding can create dangerous electrical hazards and increase the risk of electrical shock. Regular inspections of the main bonding jumper and other grounding connections are recommended to ensure they are in good condition and properly connected. Look for signs of corrosion, loose connections, or damage to the conductors. If any issues are found, they should be addressed promptly by a qualified electrician. Understanding the function and importance of the main bonding jumper is crucial for electrical safety. It's a critical component that helps to protect people and property from electrical hazards. Always follow the manufacturer's instructions and adhere to the NEC requirements when working with electrical panels and their grounding systems. The ampacity of a 10-32 screw is not a simple, fixed value that can be easily looked up in a table or chart. It's a complex characteristic that depends on a multitude of factors. Therefore, relying on such a screw for a critical safety function like a main bonding jumper is highly discouraged. The primary factors influencing the ampacity of a 10-32 screw are firstly, the material composition. Copper and aluminum alloys generally offer higher conductivity and therefore higher ampacity compared to steel or other metals. The specific alloy used also plays a significant role, as different alloys have varying conductivity properties. Secondly, the screw's dimensions, including its length and diameter, influence its resistance. A longer screw presents a longer path for current flow, increasing resistance and reducing ampacity. Similarly, a smaller diameter reduces the cross-sectional area available for current flow, also increasing resistance and lowering ampacity. Thirdly, the ambient temperature affects the screw's conductivity. Higher temperatures increase the resistance of the metal, thereby reducing its ampacity. The temperature coefficient of resistance varies for different materials, so the impact of temperature will differ depending on the screw's composition. Fourthly, the connection quality is paramount. A loose or corroded connection significantly increases resistance at the contact point, drastically reducing the effective ampacity. Even a small amount of corrosion can create a high resistance barrier, limiting current flow. Fifthly, the method of installation affects heat dissipation. A screw that is tightly fastened and in good contact with a heat-sinking surface will be able to dissipate heat more effectively, allowing it to carry more current than a screw that is poorly installed or isolated. Lastly, the presence of other nearby heat sources can influence the screw's temperature and therefore its ampacity. If the screw is located near a hot component, its temperature will increase, reducing its ability to carry current. Given these numerous and interacting factors, it's impossible to provide a single, reliable ampacity value for a 10-32 screw. Furthermore, using a small screw like this for a critical grounding or bonding application is highly inappropriate for several reasons. Firstly, the ampacity is too low and uncertain. Even under ideal conditions, a 10-32 screw will likely have a limited ampacity far below what's required for a main bonding jumper. The actual ampacity will vary significantly depending on the factors listed above, making it impossible to ensure adequate performance. Secondly, the mechanical strength is insufficient. A small screw like a 10-32 screw is not designed to withstand the mechanical stresses associated with high fault currents. The screw could break or deform under fault conditions, compromising the integrity of the grounding connection. Thirdly, the connection reliability is questionable. Small screws are prone to loosening over time, especially under vibration or thermal cycling. A loose connection will significantly reduce the ampacity and could lead to a complete loss of grounding continuity. Fourthly, the code compliance is not possible. Electrical codes, such as the NEC, specify minimum sizes for grounding and bonding conductors based on the size of the service entrance conductors. A 10-32 screw would never meet these requirements. Therefore, using a 10-32 screw as a main bonding jumper is a dangerous and code-violating practice. Instead, always use appropriately sized and listed grounding and bonding conductors that meet the requirements of the electrical code and the equipment manufacturer's specifications. These conductors are designed and tested to safely carry fault currents and maintain grounding continuity under a variety of conditions. The main bonding jumper within a UL-listed panel is a specifically designed and tested component that meets stringent safety standards. The panel manufacturer selects the appropriate size and material for the bonding jumper based on the panel's rating and the expected fault currents. UL then tests the panel, including the bonding jumper, to ensure that it can safely withstand fault conditions without overheating or failing. This testing provides assurance that the bonding jumper is adequate for its intended purpose. Therefore, it's essential to rely on the UL listing and the manufacturer's specifications when it comes to the main bonding jumper. Do not attempt to replace it with a makeshift solution like a 10-32 screw. This could compromise the safety of the electrical system and create a significant risk of electrical shock or fire. In summary, the ampacity of a 10-32 screw is highly variable and unreliable. It's not suitable for use as a main bonding jumper or any other critical grounding or bonding application. Always use appropriately sized and listed conductors and follow the manufacturer's specifications and the requirements of the electrical code.